pick some quantity of plastic, I pick some quantity of steel, and I make a toy. Let's say I have a toy factory. How many different kind of toys I can make out of wood, steel, and plastic with different, obviously, combinations? I mean, a lot. Let's say there is another competitor of mine who said, I can make many more toys than this person because I have not only the raw wood, not only the raw plastic, not only the raw steel, I have wooden frames and wooden doors as well. So at the end of the day, that my competitor cannot make more toys than me because whatever wooden material he is claiming to have, that can be made by raw wood material. And that is not a constituent, that is not an independent ingredient, that is not something that the others cannot achieve, because if others cannot achieve that thing, then that new thing is contributing a new dimension in it. Make sense?
Yes.
So because this vector 2, 3, it is generatable by this and that, it will not produce something new, and the span set will stay the same. Yes, no?
Yes.
So, and by the way, if this vector is producible by these two, then we say this vector for its production depends upon these two. Yes, no? So let me define linear independence and dependence. If V4 is generatable by V1, V2 and V3, then V4 is called to be linearly dependent upon V1, V2 and V3. So this vector is linearly dependent upon V1, V2 and V3. Yes? Okay. Now what do we mean by linearly independent set? Linearly independent vector. For example, if I give you two vectors like this, just a simple example, and I ask you, use these two, no matter what linear combination you come up with, produce this vector. Now the question is, can you produce this vector using these two? Then we say this vector is linearly independent from these two. Make sense? Yes, no? So linearly independent vector means it is not generatable by the others. What do we mean by linearly independent set? If we have some vectors in a set, then linearly independent set means every vector of that set is not generatable by the rest. So they all are linearly independent from each other, which means they are all very good contributors. Each and every vector of that, if you have a linearly independent set, each and every vector of that set has something on its own. It has not the properties that बाकी सारे मिलके भी वो चीज जनरेट नहीं कर सकते, ये जो ये जनरेट करेगा. Yes? Yes, no?
Yes.
Yes, sir. मैं तेज रहा लेकिन because you have already seen these concepts in LA, so because I'm refreshing these, so I guess still you can ask these. By the way, so dimension किसी वेक्टर स्पेस की क्या होगी? किसी वेक्टर स्पेस की dimension वो होती है the maximum number of linearly independent vectors that spans that set. दोबारा से देख लें, किसी भी वेक्टर स्पेस की dimensions क्या होती हैं? Dimension is a number. It's a positive, non-negative integer. It's a number. And dimension is the number, and that number is equal to the maximum number of linearly independent set that spans the space. Maximum number of linearly independent set. Maximum number of vectors in the linearly independent set. So, मैं ये गलत कह गया हूँ अंग्रेजी में. दोबारा से मैं कह रहा हूँ. It's the cardinality of the linearly independent set that spans the space. By cardinality it means the number of vectors in that set. For example, this space xy, how many maximum number of linearly independent vectors you can come up with that generate this space? The answer is 2. And that is 1, 0 for example, and 0, 1. These two are independent. You add a third vector here that depends upon these two.
Yes.
Make sense? Yes or no? So the independent set that spans this space, as long as the set is independent, the spanner set is independent. Count the number of vectors in the spanner set, that is the dimension of the vector space. जिसको span किया गया. Having said that, the spanner set is not unique. You can span the space using this. You can span that space using this. You can span the same space using these two, and these two are independent of each other. This is not scalar multiple of this is not scalar multiple of that. That's an independent set. It can span this, I can prove it. This can span this, but both will be having number of vectors exactly equal. That is true. That is the dimension. No matter how many independent sets you come up with that span the same space, every independent set will be having same number of vectors in it, and that same number is called dimension. Second thing, because there are several different spanners, there are several different axes to measure the positions in the vector space. ये जो spanner vectors होते हैं, ये जैसे 1, 0, 0, 1, they are called bases. They are technically, अगर आप ज़्यादा layman terms में use करें तो they are axes. First basis, second basis. And किसी एक location को measure करने के लिए किसी एक space में सिर्फ एक set of axes नहीं होता. You can have several set of axes. और ये axes आपस में orthogonal होना जरूरी नहीं है.
अच्छा.
They need to be independent.
That's it.
That's it. So it is convenient to work with independent axes. It is convenient to work with independent axes. But having independent axes is not the restriction. You can, as long as the axes are independent, as long as the vectors are independent, you can measure each and every point using those. But working with orthogonal axes or perpendicular axes is convenient. Yes, no?
Yes.
So far so good?
जैसे ये जो दो हमने वेक्टर बनाया ये लाजमी नहीं है कि ऑर्थोगोनल हो.
ये ऑर्थोगोनल है नहीं, इनका डॉट प्रोडक्ट इज नॉट जीरो.
डॉट से ऑर्थोगोनल के लिए डॉट जीरो की होने की प्रॉपर्टी है.
ऑर्थोगोनल के लिए यूक्लिडियन स्पेस में डॉट जीरो होना जरूरी है, और अगर आपने अपना कोई डॉट डिफाइन किया हुआ है तो वो वाले डेफिनेशन के लिहाज से रिजल्ट जीरो आना चाहिए. यार समझ आ गई? सही से कितना? Am I going too fast or is that okay? Going too fast? If you take dot from these two, that is zero. That means these two are perpendicular of each other. If you take dot from these two, the answer is not zero. They are not perpendicular of each other. Okay? But these two can also act as axes to measure pole to be. So वो एक्सिस जिसके लिहाज से आप मेजरमेंट करते हैं उन एक्सिस का ऑर्थोगोनल होना जरूरी नहीं है, परपेंडिकुलर होना जरूरी है. अगर परपेंडिकुलर हो तो दिस इज गुड, एडेड एडवांटेज. यस. सो मैं नतीजा इस बात की सबको दोहराता हूँ, फिर हम आगे चलते हैं. नंबर 1, वेक्टर स्पेस एक सेट होता है जिसकी कुछ खास प्रॉपर्टीज होती हैं. किसी भी सेट का अगर आप स्पैन लें यानी सारे लीनियर कॉम्बिनेशंस ले लें तो जो स्पैन्ड सेट होगा वो वेक्टर स्पेस होगा डेफिनेटली. उस वेक्टर स्पेस की डायमेंशंस क्या होंगी? स्पैनर सेट अगर लीनियरली इंडिपेंडेंट है तो वो कितने हैं उसमें इंडिपेंडेंट वेक्टर्स, और अगर वो लीनियरली इंडिपेंडेंट नहीं है स्पैनर सेट तो ऑब्वियसली जो स्पैनर सेट है उसमें नंबर ऑफ डायमेंशन से ज़्यादा वेक्टर्स होंगे. तो फिर उसमें लीनियरली इंडिपेंडेंट वेक्टर्स काउंट कर लें कितने हैं. देयर इज वे टू फाइंड आउट लीनियरली इंडिपेंडेंट सबसेट ऑफ अ सेट. यानी अगर मैं आपको सेट ऑफ वेक्टर्स दूं एंड आई आस्क यू फाइंड आउट द मैक्सिमल लीनियरली इंडिपेंडेंट सबसेट ऑफ इट, देयर इज अ क्विक एल्गोरिथम टू डू दैट. यस, मेक सेंस? सो डायमेंशन ऑफ, ये मैं लेमन टर्म्स में अब मैं आपको अंडरस्टैंडिंग वे में थोड़ा सा बताता हूँ मैथमेटिक्स से. किसी भी स्पेस की डायमेंशन से क्या मुराद है आप वो एक बकेट लें, बकेट एल्गोरिथम सॉल्व, एक बकेट लें, स्पेस में घुस जाएं, एक वेक्टर उठाएं, बकेट में डाल लें, आप स्पेस के अंदर हैं, कोई और वेक्टर उठाएं, वो बकेट में डाल लें, लेकिन ध्यान में रखें बकेट के अंदर कभी भी डिपेंडेंस नहीं आनी चाहिए। बकेट शुड कंटेन ऑलवेज इंडिपेंडेंट वेक्टर्स। सो जब आप नया वेक्टर डालेंगे मेक श्योर कि वो बाकियों से इंडिपेंडेंट है, और जो ऑलरेडी उसके अंदर है वो एक दूसरे से इंडिपेंडेंट है। कीप फिलिंग द बकेट। जब आप वेक्टर स्पेस में घूमते घूमते उस बकेट को इतना फिल कर लें कि मजीद कोई भी वेक्टर उसमें ऐड ना किया जा सके। अब जो भी नया लेके आते हैं डिपेंड्स अपॉन द रेस्ट, नो मैटर व्हाट यू डू। तो अब जो बकेट का साइज है ना, दैट इज डायमेंशन ऑफ द वेक्टर स्पेस। सो किसी भी वेक्टर स्पेस की डायमेंशन क्या होती है, उसमें से मैं कितना बड़ा पूल सेलेक्ट कर सकता हूँ इंडिपेंडेंट वेक्टर्स का। मेक सेंस? सो याद रखें, अगर आप 5 डायमेंशनल स्पेस में बैठे हुए हैं तो यू कैन नॉट कलेक्ट 6 इंडिपेंडेंट वेक्टर्स फ्रॉम इट। दैट्स व्हाट आई एम सेइंग। Yes, no? Yes. Clear? Yes. Is that okay? Okay, last things about vector spaces. Subspace. A subspace is a subset that itself is a vector space. So for example, एक सेट है बहुत बड़ा, उसके अंदर से आप कुछ वेक्टर्स उठा लें, सबसेट, और उस सबसेट को देखें, it is also closed under scalar multiplication, it is also closed under addition. That subset also is a vector space ना, क्योंकि अब मेरे पास एक सेट है और वो closed है under scalar multiplication, closed under addition. So that is also a vector space. So उसको कहेंगे वो parent space है, ये उसकी subspace है। इसकी भी अपनी कोई dimension होगी, मैं मिसाल देता हूँ। मैं बिल्कुल सिंपल एग्जांपल्स ले रहा हूँ। These are bases of three-dimensional space. By bases means like axes or independent vectors that span the space. That's a three-dimensional space. Now consider a subset that is span of these two. Consider a subset in three-dimensional space, and that subset is span of just these two. That's a proper subset because this is not contributing. Make sense? That subset itself is a vector space. Why? Because it is span of a set. समझ आ रही है? और उस सबसेट की जो डायमेंशन होगी वो 2 होगी, क्योंकि उसमें मैक्सिमम नंबर ऑफ इंडिपेंडेंट वेक्टर्स होंगे। में आ गई? एक स्पेस के अंदर यानी एक सेट के अंदर एक सबसेट हो सकता है ऐसा। आप एक स्पेस बना रहे हैं 50 वेक्टर्स लेके, 50 के 50 इंडिपेंडेंट, तो एक स्पेस बनेगी 50 डायमेंशनल। यस? उस 50 डायमेंशनल स्पेस को आप देखें, बहुत बड़ी स्पेस है, इन 50 में से कोई से 10 ले लें और उन 10 से एक स्पेस बनाएंगे। वो स्पेस उस 50 डायमेंशनल स्पेस के अंदर रहेगी। ये सारे वेक्टर जो इन 10 से बनाए जा सकते हैं वो 50 डायमेंशनल स्पेस के अंदर हैं। अब इन 10 से जो आपने बनाई है दैट्स अ सबसेट ऑफ 50 डायमेंशनल स्पेस, लेकिन ये सबसेट इटसेल्फ एक वेक्टर स्पेस है क्योंकि ये स्पैन ऑफ अ सेट है। सो एक वेक्टर स्पेस के अंदर बहुत सारी सबस्पेसेस होती हैं। फॉर एग्जांपल यू हैव 3 डायमेंशनल स्पेस, देयर आर इन्फिनिटी मेनी 2 डायमेंशनल स्पेसेस इन इट, देयर आर इन्फिनिटी मेनी 1 डायमेंशनल स्पेसेस इन इट, and there is a 0 dimensional space as well. I'm not going to talk about that. Okay? Yes, no? चूंकि वेक्टर स्पेस के लिए 0 वेक्टर होना लाजमी है, ये याद रखिएगा। A set not containing 0 vector is not a vector space, no matter how big it is. हमारे ज़हन में तो बहुत ज़्यादा वेक्टर ना ये स्पेस है, नहीं। A set not containing 0 vector is not a vector space. A set containing 0 vector may be a vector space, maybe not. We have to check it.
आप ये कह रहे हैं कि पीवी हमारे पास जैसे स्पेस उसमें कभी 1 डी है उसकी इनफाइनाइट स्पेस।
Yes.
इनफाइनाइट स्पेस कैसे, मतलब हमारे पास एक है तो उसके हम सारे केसेस स्पैन हो रहे हैं जिसमें यूज किए।
No. So let me explain that. Consider a line here for cosmic here. That's 2-dimensional space x, y. The basis of this space is 1, 0 and 0, 1. Consider this line that is passing through origin. Every point on this line is the velocity here. Every point on this line is a scaled version of this vector. Which means every point on this line is generatable through one vector. Yes? Okay. So this one vector acts as the basis of this space. And this is a vector space because every vector is scalar multiple of the other. You choose this one, you add these two, you get a point on this. You choose any one of these, you scale it, you stay on this. So that's a vector space in itself. But to generate this vector space, you only need one axis, one direction. And you scale that and you make all these points. So that's a one-dimensional space. Now consider another one-dimensional space. Consider another one-dimensional space. Consider another one-dimensional space. Each one-dimensional space will be having its basis. There are infinitely many one-dimensional spaces in this 2D. Make sense? Because a vector space has to contain zero vector, this line is not a vector space, although it has infinitely many points. It is a line, it is not a vector space. It is a set of infinite vectors, but it is not a vector space. Make sense? So consider this. If you have a 3D space, every plane that is passing through origin is a vector space. It's a 2D vector space. Every line that is passing through origin is a 1D vector space. A plane that is not passing through origin is not a vector space. Remember that. So far so good? Yes. Okay, I'm moving on. This is matrix A, okay? If I multiply these two, I can get several things, but one thing that you notice is this. That product ends up having this form. If you multiply these two and represent the addition, that addition can be represented in this way as well. Convince yourself this is the case. I mean, you can write x1 plus 2x2 plus x3, that's the first component of the product. Then second component, then third component. You can rewrite these components in this form. Yes, no? Yes.
ये आप आपने खुद डिफाइन किया, right?
No, I'm writing, I'm saying that this product is exactly equal to that.
9.
Yes. Let's see.
Oh, okay.
I mean, you rewrite these components in this way.
Okay.
Make sense? Yes, no?
Yes.
And what is this? Can you tell me what is this? It's a linear combination of the column vectors. When you are solving a linear system, all you are doing is you are checking whether this belongs to column space of the matrix or not. That's what you check. Because on the left hand side, it's a linear combination of the columns. And if the linear combination of the columns of the matrix, if it can generate this thing, if columns can generate right hand side, then the system has solution, not otherwise. So when you solve a linear system, you actually check whether the right hand side, it belongs to column space of A or not. So, in summary, if AX equals to B has a solution if B belongs to column space of A. And what do we mean by column space of A? It is spanned by the columns of A. What do we mean by row space of A? It's spanned by the row vectors of A. Yes, no?
Yes.
Now the second question, now the important question is, what is the dimension of the column space? What is the dimension of the row space? You tell me, what is the dimension of the column space? The total number of independent columns. What is the dimension of the row space? The total number of independent rows. And that number, the total number of independent columns, is equal to, I'm saying this without proof, the total number of independent columns of a matrix is always equal to the total number of rows, independent rows of a matrix. And that number is called rank of the matrix. What do we mean by rank of the matrix? It is the total number of independent columns of a matrix. So अगर आपको कोई बताए कि मेरे पास एक matrix है 50 by 50 और उसका rank है 3, you can blindly say only 3 columns are independent. The other 47 they are generatable by these 3.
The total number of pivots
Total number of pivots की ये चीज़ है, exactly ये चीज़ है. Actually pivot के through ही find out करते हैं they are independent. Independence establish कैसे करते हैं by logical form. So far so good? Yes, no. Yes. Okay. So rank of a matrix is equal to dimension of the column space of the matrix. Rank of the matrix is equal to dimension of the row space of the matrix. And dimension of row space and dimension of column space of any matrix, they are equal. I'm stating this without proof. There is a proof of it. Actually, the proof is the following. Rank of A is always equal to rank of A transpose. And there is a proof for that. There is a proof for that. Make sense? Okay, I move on. I still have some more steps. I should move towards null space.
single pivot of the
Sorry, pivot. Pivot. There is a process of converting a matrix to a particular triangular form or a rectangular form. In that form, the first non-zero entity of every row is defined as pivots. Once we define that as pivots, it has certain properties that tells you something about independence among the row vectors and column vectors. So, quickly, and it gives us a message. 4, 1, 3, 9. You can consider this matrix as a transformer that transforms this point to another point. So when you apply this matrix to this one, it maps this vector to some other vector. And you can now imagine if the matrix has just 2 rows and 3 columns, then this 3D point will map to a 2D point. And if this matrix has 4 rows and 3 columns, then this vector of 3 components is uplifted to a 4D space. So you can map points of one space to another space. And this kind of mapping that is achieved by matrices is called linear mapping or linear transform. Clear? So you can consider this as a transformation. Matrix is a transformation, linear transformation that maps this to something else. For some matrices, there might be a lot of vectors that all get mapped to 0. There might be some vectors given a matrix. For example, if I ask you, I give you a matrix, find out all the vectors that get mapped to 0. When they are transformed, they all map to 0. समझ आ रही? These vectors, all of them, whether it's a single vector or infinitely many, these vectors are called the null vectors of matrix A, and set of these vectors, we can prove that's a vector space, which is closed under scalar multiplication and addition. That space is called null space of A. मैं दोबारा से बताता हूँ. What do we mean by null space of A? It is a set of all vectors that are transformed to 0. So अगर मुझे एक मैट्रिक्स दिया गया है, मुझे कहा था इसकी null space फाइंड आउट करें. Find out the null space of it. तो मुझे वो तमाम वेक्टर्स फाइंड आउट करने हैं जो 0 पे मैप हो जाए. So अगर मैं null space डिफाइन करूँ किसी मैट्रिक्स की तो ऐसे डिफाइन करूँगा. null space of a matrix A is the following. Null space of a matrix A is all x such that Kx is equal to 0. This is null space of matrix A. All vectors x that are mapped to 0. समझ आ रही है?
Yes.
अगर आवाज से देखिएगा, अगर मेरे पास एक 3x3 मैट्रिक्स हो और उसका रैंक 3 हो, which means कि उसकी कॉलम स्पेस 3 डायमेंशनल है. That means कि अगर मैं उसको कोई 3D का पॉइंट दूंगा तो वो जो जवाब जनरेट करेगा वो एक 3D में जाएगा, and that 3D is a कॉलम स्पेस. सही है? मैं अगर सारी डोमेन देखूं उस फंक्शन की या ट्रांसफॉर्मेशन की, दैट्स अ होल 3D. और अगर मैं उसकी रेंज देखूं, यानी ये जनरेट क्या क्या कर सकता है, बिकॉज ऑफ रैंक इज 3, दैट इज आल्सो 3D. सो कोई भी मल्टीपल पॉइंट्स ऐसे नहीं होंगे जो 0 पे मैप हो जाए. अब ऐसा है ना, ये मेरी बात समझ आ रही है? पूरा गौर से देखिएगा. अगर मैं 1-to-1 कॉरेस्पॉन्डेंस एस्टैब्लिश कर लूं, यानी मेरे पास एक कॉलम स्पेस है जो 3D है और मेरे पास एक ओरिजिनल स्पेस है जो 3D है. चूंकि किसी मैट्रिक्स का रैंक अगर 3 है और वो 3x3 मैट्रिक्स है, तो वो 3D को 3D पे मैप करेगा, यानी उसकी कॉलम स्पेस चूंकि 3D है तो वो 1 by 1 वेक्टर लेता जाएगा 3D से, और उनको जब मैप करना शुरू करेगा तो जब सारे वेक्टर्स मैप हो जाएंगे, दैट विल बी अ फुल 3D कॉलम स्पेस. यस, इसका मतलब है कि कोई जो ओरिजिनल स्पेस है उसमें कोई इन्फिनिटली मैनी वेक्टर्स या बहुत ज़्यादा वेक्टर्स या 2 वेक्टर्स एटलीस्ट ऐसे नहीं थे जो किसी एक पॉइंट पे मैप हुए, क्योंकि दिस इज अ 3D, दिस इज अ 3D, दे आर 1-to-1 कॉरेस्पॉन्डेंस बिटवीन ईच अदर, दे आर सेम यूक्लिडियन स्पेसेस. अगर कोई 2 वेक्टर्स किसी एक पॉइंट पे मैप होते तो ये फर्क इसके नंबर ऑफ पॉइंट्स कम होते, इसके ज़्यादा होते. मेक सेंस? तो ऐसा मैट्रिक्स जिसका रैंक फुल है, 3x3 मैट्रिक्स है, उसका रैंक भी 3 है, और यानी उसकी कॉलम स्पेस फुल डायमेंशनल है, 3 डायमेंशनल, उसकी नल स्पेस एम्प्टी होती है. उसमें मल्टीपल पॉइंट्स नहीं होते जो 0 पे मैप होते. याद रखें, बहुत सारे पॉइंट्स 0 पे कोलैप्स होंगे तो हम कहेंगे मैट्रिक्स की नल स्पेस एग्जिस्ट करती है, वो सारे पॉइंट्स जो 0 पे कोलैप्स होते हैं. और जब मैट्रिक्स का रैंक फुल होता है, नल स्पेस डजंट एग्जिस्ट. The only vector that maps to 0 is 0 itself.
Yes.
There is no other vector. And there we say the null space actually doesn't exist. It exists in a trivial form, 0, 0, 0, but it doesn't exist in an interesting form. तो जब मैट्रिक्स का रैंक फुल हो तो जो आपकी डोमेन है और जो आपकी रेंज है वो दोनों डायमेंशन सेम होती है और मैट्रिक्स इनवर्टेबल होता है. यानी अगर आप इस स्पेस को इस पे मैप कर सकते हैं विदाउट मैपिंग 2 पॉइंट्स टू 1 पॉइंट, देन यू कैन गो बैक. और याद रखें, जब मैट्रिक्स का रैंक फुल होता है, इक्विवेलेंटली जब मैट्रिक्स की नल स्पेस नहीं होती, देन द मैट्रिक्स इज इनवर्टेबल.
Yes.
Not otherwise.
Yes.
The transformation can be inverted. Make sense? एक और चीज और से देख लें, बस मैं खत्म कर रहा हूँ. I need to continue this session on, let's say, Friday or early next week. This session is important, I guess, because I'm missing extremely important concept of eigenvalues and eigenvectors. I have to cover that, and then next week is singular value computation. I guess I understand covering all that concepts in 1 hour is not possible, so I want another hour, maybe another hour after that. But I guess we should have a couple of sessions on this. So yeah, just let me finish this by telling you one thing, that if this vector is if this vector is mapped to 0, there are several vectors like this that are mapped to 0, and all those vectors will make a space called null space. Every vector of null space, you can notice it is orthogonal to every row. Yes? If this is a null vector doesn't mean it's a vector of zeros. Null vector means it maps to null vector. If this is a null vector, then it must be orthogonal to row vectors. And we can easily conclude that null space is orthogonal to row space. You come up with any null vector, it will be perpendicular to all the row vectors and so their span.
अच्छा
Make sense? अगर वो स्पैनर के परपेंडिकुलर है तो स्पैन के भी परपेंडिकुलर होगा।
बिल्कुल सही। वही लाइन आप एक्सटेंड कर रहे हैं ना, तो उससे तो
सही है? So this null space and row space they are orthogonal. और हम अगले इंशाल्लाह सेशन में देखेंगे they are not just orthogonal, they are orthogonal complements. By orthogonal complements I mean कि अगर full paired space 5D है तो उसमें 3D अगर row space ले गया तो 2D null space ले जाएगा. So their dimension sum will be equal to the dimension of the paired space. They are called complements, orthogonal complements. Okay, we will continue from here onwards inshallah in the next session. Next session announce कर दिया जाएगा. Next section is more important because it describes the eigenvalues and eigenvectors. For eigenvalues, eigenvectors without telling you spaces is difficult to communicate. Okay? So we are having one more session. I guess one more, that's it. Okay.